So dear students, in this video I'll be talking about, rather I would like to discuss the Fermi level in intrinsic semiconductors. So we would like to discuss that what could be the most probable position for the Fermi level between the valence band and conduction band of an intrinsic semiconductor. As we understand that in case of intrinsic semiconductor, we have the number of electrons that are available for the conduction. That's equal to the number of holes that can be created in the intrinsic semiconductor. Now, in intrinsic semiconductors, the probability of finding an electron in the conduction band. So if I draw an energy band diagram, and if I assume that this is my valence band, and there is a Fermi level, an arbitrary position I'll take here, and then we have the conduction band. Okay, so this is my valence band, and this is my conduction band. Now, as I said that in case of an intrinsic semiconductor, the probability of finding an electron in the conduction band is zero, and the probability of finding a hole in the valence band is zero at absolute zero. So that means an intrinsic semiconductor behaves as a pure insulator if we have the system at absolute zero. So as we increase the temperature of these intrinsic semiconductors, there is equal number of electrons and holes, right? That get generated, and in such case, the Fermi level can be given as, if I say that EF is the Fermi energy. This Fermi energy, if I assume here that the energy linked with valence band is EV, and the then talking about the Fermi energy in this case, this Fermi energy comes out to be the average of EC and EV. So the target of the present lecture is to achieve this expression for the Fermi energy in case of an intrinsic semiconductor. So what happens basically is, when we increase the temperature, so your Fermi level will be exactly here. Okay, as we increase the temperature, there is availability of what we call as electrons in the conduction band goes on increasing, and we have holes that are created in the valence band. So this is my Fermi level, and at absolute zero, this Fermi level is it's like this. Okay, so this is I should call it T is 0 Kelvin. But as we increase the temperature, say for example, we take the system to a temperature of 40 degree. say for the sake of argument, then you can see here that there's a bending of energy like this. And this is, okay, no, this has gone wrong here. This has to go through the Fermi level. Sorry. Okay, this one is the correct one. So we can see that there is the splitting of this. There is the bending of this Fermi energy as we increase the temperature. So this part should not be taken. So at 0 Kelvin, the Fermi energy is exactly like this. But if we take the system to a temperature of 40 degrees Celsius, then we can see that we have the bending of this Fermi energy, and you have electrons in conduction band, and the equal number of holes will be generated at the valence band. Okay, so this is the energy band. This is the energy band diagram for intrinsic semiconductor. Okay. Now let's move on from here. Now, as we understand that we are dealing with the electrons in these materials, and we have the applicability of Fermi-Dirac statistics, and we better understand for an intrinsic semiconductor this N is equal to P, the number of electrons is equal to the number of holes, and we can approximate that equal to Ni. So Ni will be same for electrons, and Ni will be same for holes. Now, if we have to write down the Fermi-Dirac distribution function for electrons and holes, the two functions should be exactly equal to each other. So in order to do that, let me assume that NC is the number of electrons in conduction band, and NV is number of holes in valence band. And if that's the case, and if I assume that EC is the energy of the top of the conduction band, EV is the energy of valence band, and EF is the Fermi energy. So this is energy of conduction band, this is energy of valence band, and this is energy of what we call as Fermi energy. Now, as I said, that the Fermi distribution function must be same for electrons and holes. So if I have to write here, I would write NC e to the power of minus times E for conduction electrons, it's EC minus EF divided by kBt. Okay, so since we are dealing with the same temperature at some particular temperature, so temperature will also be same for the two system of electrons in the conduction band and system of holes in the valence band. So for this is for electrons here. So for holes it is NV e to the power of minus EF. It will start from EF minus EV times divided by kBt, where this K is the Boltzmann constant, right? So this gives me the distribution of electrons in the conduction band, and this gives me the distribution of holes in the valence band. Since we are talking about an intrinsic semiconductor, so the two distributions can be equalized with each other. So if I simplify this, this is Nc by Nv equal to, we can have e to the power of minus times Ec minus Ef by kBt divided by e to the power of minus Ef minus Ev divided by kBt. So this will be my equation, and I would like to have a simplification in my right hand side. So to move on from here, we have here 3. So Nc by Nv. So what's it going to be equal to? So this is equal to e to the power of, okay, minus times e minus times, if I take it up, so what will be my relation? It will be Ec, this should be Ec, okay, this will be plus, then plus Ev, okay, and then minus 2F, yeah, and this will be plus. When you will solve this, you will get the same thing. So this is divided by kBt, right? Now, so I can have Nc by Nv equal to e to the power of, I will write it again, Ec plus Ev minus twice Ef divided by kBt. All right, and if I apply log on both sides, so applying log on both sides, I'll get log of Nc upon Nv is equal to Ec plus Ev minus twice Ef divided by kBt. And this should be the case. All right. So, so we can move on from here. What we'll write Ec plus Ev minus twice Ef will be, yeah, this kBt will go up. This is kBt log of Nc by Nv. Okay, this should be the outcome. Now, if I keep this twice Ef here, so this is minus. Let me write minus twice Ef. Yeah, this will be, this Ec will go other side. This will become minus Ec. This will become minus Ev, and we have already here kBt log of Nc by Nv. Okay, so let us multiply this equation by minus from both sides. So what are we going to get from there? We will have twice Ef equal to, this will become plus, this is Ec plus Ev, okay, then plus kBt log of Nc by Nv. Okay, so this is the point, and we can immediately think of Ef for my energy. This is Ec plus Ev divided by 2 plus kBt log of Nc by N0 divided by 2. Now, now if this Ni is exactly equal to Nc, okay, if this is Nc and Nv, if this Nc is equal to Nv, so if that's the case, this term is going to die, and we will have the expression for Fermi energy, and that will be EC plus EV divided by 2. So this was our target equation, and this target equation is telling us that this Fermi energy will lie in the forbidden energy gap. So we have the conduction band and we have the valence band. Now this Fermi energy will lie between conduction band and valence band, and its value will be given by EC, the energy of the conduction band, plus energy of the valence band divided by 2. So this is going to be at the middle of the two bands that we have been talking here.